Alright guys, similar to last week, we're going to continue on our trail for our decision tree. So just to go over the flowcharts for t-tests, again, for t-tests we're going to have a single parametric dependent variable. In looking into our independent variable type, okay, it should be classified as non-parametric or nominal data. We should only have one independent variable, and when we investigate further how many groups we are splitting this independent variable into, it should only be two. Okay. When we have two levels of a single independent variable matched with a single dependent variable measurement, we're going to be using a t-test. Okay. If we have between subject or different subjects being measured for each sample, we would use an independent t-test. If we have different subjects or the same subjects being used or within subject comparison or study design, we use a paired samples t-test. Okay. I've listed the assumptions. Both of these should be pretty much the same, right? Where we have normal distribution, random sampling. We'll have parametric dependent variable in addition to two levels of non-parametric independent variable. Okay, so you could add that if you want to. For an independent t-test specifically, we're looking at homogeneity of variance. And I can further specify this saying that we use Levine's test. So you might have to add that to your flow chart. Okay. And then over here, technically when we look at the correlation between our values in our paired samples t-test, this is also evaluating homogeneity of variance, meaning that the variance between our samples is similar enough such that we end up with a strong positive correlation. Okay, so on a test, if you wrote homogeneity of variance, that's fine, as long as you indicate the distinction between paired and independent t-tests, such that independent t-tests we measure homogeneity of variance with the Levine's test, versus a paired samples t-test we evaluate using the correlation between the dependent variable measurements for the groups that we're investigating. Okay, so decision tree is fairly straightforward for t-tests. As far as the output, we do get a little bit more complicated from, actually I think we kind of take an easier step, so maybe a step backwards, slightly different concept than regressions, but it's a little bit less busy for you guys. So I've split up the page. Top portion is how you would read an independent t-test. The bottom is what you would get in an output for a paired samples t-test. Okay. You will notice that each of these dotted boxes will represent areas of your output that have a p-value. So you kind of can use that to reference back to your outputs, but also note that I do not have a flow for a single sample t-test. Generally, we're not going to use those as much in the class, even though they are important to cover. So, and also those ones are easier to read. They're a little bit more straightforward, so I don't think you need the extra supplementation for those ones. But generally when we run an independent t-test, we have to make sure we have homogeneity of variance. So we have to look at Levine's test first. Okay, that will tell us, or that will give us a p-value that basically tells us if we have relatively equal variances between our samples, which is basically just going to be looking at whatever our measure of variability is. Is that measure of variability, typically it's standard deviation, right? But we know that standard deviation is very similar to variance, so the actual equation that kind of crunches through this test is slightly different than as something as simple as looking at, well, what's the standard deviation of sample 1 compared to sample 2? But in essence, that's what we're looking at, right? And in order for our samples to be considered comparable, our variances have to be relatively similar. So if we look at the p-value for Levene's test or for homogeneity of variance test, it's either going to be greater than 0.05 or less than 0.05. Oh, hello, father. Anyways, he supplements my life with California pictures. But we get this p-value for Levene's test. Okay, and again, all of our tests are going to be run using a 95% level of confidence. Okay, so if p ends up being greater than 0.05, right, and this, we get exact p-values in our output. So you're just kind of relating that value to how it would pair up with 0.05, right? If that p-value is greater than 0.05, we accept the null hypothesis, which would say that we have relatively equal variances, right? Or we can assume that we have equal variances, which is the assumption that we're trying to prove, okay? So in this case, a p-value greater than 0.05 is really desirable, okay? Because that means we've collected a pretty good sample. In the case that we have p-values for this Levene's test that are less than 0.05, that would indicate we have to reject the null hypothesis for Levene's test, in which case we would say we have unequal variances, right? Or we can't assume that we've met this homogeneity of variance assumption. So based on what the p-value is for Levene's test, that will tell you which row to read in your output, right? You'll have an equal variances assumed row, and you'll have equal variances not assumed row. And so in whatever row you read, you're looking at the t-test, right, or the t-test results, which is where you'll find your p-value for the t-statistic. Okay, so in this case, remember, t-tests are going to be evaluating differences between the means. So if we're looking at a null hypothesis, we would say the difference between the means is not significant. We could say there's no effect of whatever the treatment is, right? Or there's no significant difference between groups. Something kind of generally getting at that idea, right? We could also say that the mean, or the difference between the means is not different enough such that we could conclude our samples were taken from the same population. Okay, so there's a lot of different ways that we can word this, which is nice because you kind of just pick your favorite way and then you use that for the exam. So you only have to pick the one that makes most sense to you and stick with it. Okay, based off of the p-value you get for t, again, the p-value is relating back to the null hypothesis. So if your p-value is greater than 0.05, you would accept the null and say there's no significant difference between the means of the groups you're measuring. If you get a p-value less than 0.05, you would accept your research hypotheses, which are the exact opposite of the null hypotheses. Okay, so independent t-tests, pretty straightforward. For a paired samples t-test, this is when we have a within subject design, right? We have to look at our paired samples correlations first. Okay, so we'll get a p-value for R, which should be significant in most cases. Okay, but we generally want an R that is equal to, greater than, or equal to, so I can amend this slightly, greater than or equal to 0.8, and it should be a positive 0.8. Okay, but anything 0.8 or higher would indicate we have a strong relationship, which is good, right? Because similar to when looking at the variance in an independent t-test or between two independent samples, we have to make sure that our results make sense such that the pre-test measurement is relatively indicative of a person's progress in their post-test measurement, right? So we desire this R value, right? If we don't have an R value that tells us, or an R of 0.8 or above, that tells us there probably is something wrong with our sample. Maybe we copied data wrong or recorded it wrong, but either way it tells us we need to go back and reevaluate our sample. Okay. From there, if we pass this correlation test, we then look at our paired samples t-test information, where the p-value for t will be listed. Again, the null hypotheses are basically the same as up here, only your groups are going to have the same subjects in them instead of different subjects. But really we're still looking at, does the effect of the treatment work? Does or whatever the manipulation was for your group, right? Did they come from the same population? Was the difference between the means significant or not? That's pretty much the root of what this p-value is looking at, right? And so then based on that exact p-value, you can say, right, if that exact p-value given is greater than 0.05, you would accept the null hypothesis. If that exact p-value given in the table is less than 0.05, you reject the null hypothesis, okay? So like I said, t-tests, they're about as straightforward as you can get. So hopefully the flowchart helps, and hopefully this is a refreshing difference from last week. Additionally, I wanted to go through the stats summary test. You can see this is the filled out version, but I have all 3 t-tests listed. Okay, their assumptions are up here. Okay, anytime you see a yellow box, that is going to be an assumption that is tested in SPSS. Okay, so that's usually we're going to assume from here on out we have normally distributed samples and that we've randomly sampled the data that we've collected. But a lot of times, like homogeneity of variance and the correlation, you won't know those things until you actually run the test in SPSS. Okay. I also have information about your dependent and independent variables, what type of data they would be classified as well as the null hypothesis for the main effect of the test. I think from this lecture on, people sometimes get confused about what the main effect is, right? And just think about what's the purpose for running a t-test, right? It's to look at the difference between the means. So you're going to be looking at the p-value, right? That is going to be reflective of the difference between the means, which we use the t-ratio or the t-statistic to figure that out, right? So as far as the main effect, the null hypothesis is going to be paired with the p-value associated with t, right? We're going to get different p-values for the homogeneity of variance and the correlation factor, or the correlation coefficient for independent and paired t-tests. So you just have to remember each of those things is going to have its own null hypothesis, right? For every p-value, there is a null hypothesis, okay? So as long as you keep your null hypotheses sorted and you know how that p-value relates to that null hypothesis, you should stay relatively organized in your thought processes so you're answering questions correctly. Okay, as you can see, we only have 2 tests left in our ANOVAs, and we'll go over those next week. So similar to correlations and regressions, I would highly recommend going through the blank flowcharts, going through the blank sheet, or the blank versions of the stat summary sheet, and just keep filling them out and use them as a kind of a study guide or a way to test your knowledge to see if you understand stuff.